Okay, good, yeah. Here's the plan. We'll look at that problem. If you have any questions on any of the other ones, we can tackle those too, and then we'll go back to our calculation we ended the hour with last time. So this was that homework problem that I just returned, and we had the helical mass distribution. And so the helical mass distribution, if we're in free space, we'll just put it along the z-axis, right? And we're asking what are going to be the conserved quantities in the field of such a thing. Now this time, we would certainly begin with cylindrical coordinates. So we'd say, good, it's rho, phi, z, rho dot, phi dot, z dot. But this object has no cyclic coordinates as it stands. Okay. If you move in and out from it, it's definitely changing its perspective. If you go around it, it's changing its perspective. And in z direction, it's changing. Okay, so no cyclic coordinates. However, what we want to do is a transformation that leaves the view unchanged. And that transformation is we're going to go around it and up in the z direction. We're going to do a combination of phi and z so that we're climbing that, and it always looks exactly the same for that reason. Okay. So we're going to say L equals L naught plus DL. And the transformation that leaves us unchanged equals L naught plus DL d phi d phi plus dl dz dz. And what we're requiring is that equals 0. So we're requiring that this combination of things equals 0. Now, continuing then, for the helix, we can say we have z equals some height over 2 pi times phi. So every time I go around 2 pi, I go up some little height h. We can say that defines the helix. And therefore, dz is equal to h over 2 pi times d phi. So now, for this thing here, what we're requiring is that dl d phi times d phi plus dl dz. Now my dz is going to be times h over 2 pi d phi equals 0. D phi is arbitrary, and it's a common factor now, because I could go one direction or the opposite direction, but still have to get a 0. So what we're going to get is, I'll write this out. I'll write a couple lines out. dl d phi plus h over 2 pi dl dz dp equals 0. This one's arbitrary. So this is what has to equal 0. And finally, a little more room here. The dl d phi is the complete time derivative of dl d phi dot, because that's the Euler-Lagrange equation. And I'm going to do the same thing for this dl dz. That's the complete time derivative of dl dz dot. So what's conserved is what's in the square bracket. And the square bracket, you have a room up here. So for that square bracket, we would have, I'll call it piece of phi plus h over 2 pi piece of z is equal to some constant. So that's the conserved quantity. A combination of angular momentum and linear momentum in the z direction is what's conserved on the system. Okay, so that makes use of the technique we did when we were imposing transformations on our Lagrangian and requiring it to be equal to 0. Straight out of Landau with this. Okay. I can't claim credit for this one, but it's a very nice example of this whole symmetries and conservation laws business. And you know, the theme of all of these is what can you know about the system without actually solving the equations of motion. And the more you can do, the better, because equations of motion are hard to solve. Right? So get the general picture here. Good. Was there anything else on the stuff I just returned that anyone had a question about? If not, we'll go to our oscillatory problem. We can always answer other questions anytime. So, go to the problem we were working on Monday. Set that one out through a bit. That was the 2 masses, 3 strings, except with the full solution of the problem. So I'll set it up and then get to the point where we had been on Monday and see what we do. There we go. Okay, so last time we had been working on this system, okay, and there was these 2 masses, 3 springs, K prime, K, and we made considerable progress on this. So what we know is omega 1 is root k over m. Omega 2 is root k plus 2k prime over m. Really important result. The eigenvector that goes with this is 1 and 1, and the eigenvector that goes with the second one is 1 and minus 1. Okay. And we had set that problem up and solved it. So we had x1, x2 equals alpha 1, 1, 1, e to the pi omega 1t, alpha 2, 1 minus 1. Omega 2t, and then we took the real part, solved. So how far did we get? What's the very last thing you guys have? Did you write those down? Different notebook. We consult. How about over here?
We're on initial conditions.
Because I think we
got to E equals C around and A equals C.
very nice. So from here we said, okay, x1 equals a cos omega 1t plus b sine omega 1t. That was going to the real parts plus c cos omega 1t plus d oh, sorry, omega 2 sine omega 2t. And then x2 was the same thing here, minus those same ones there. And that was because of the structure with the eigenvectors. So we had done that, and we found that A equals C equals this initial condition over 2, and B equals D equals 0. I think I kind of rushed this one, but it's there. It's there in your notes. I rushed this one a bit. We had that equation. If you add the two equations, subtract them, you can show that B equals D equals 0. So I think we have that fair and square. What else? Oh yeah. I'll just state what the initial conditions were. x1 of 0 is x1 0, and everything else was 0. The initial condition of the x2 position and the initial condition of the velocities. So everything was released from rest. So that's what we had so far. And I'll just pick up where I left off and write these things out with the new constants. With room for that right here. So yeah, this was at long last solving for the actual motion of a system. We'll see some interesting results here. So now what we have is x1 of t equals x10 over 2 times cos omega 1t plus cos omega 2t, and x2 of t cos omega 1t minus cos omega 2t. Now these results, right, t equals 0, you just got to put 0, t equals 0, 1 minus 1. So you're good for that. And the derivatives are all signs, and therefore the first derivative is 0, t equals 0 vanishes. So that's a good solution. And at this level, you know, these two frequencies can be very different depending upon these two different springs. They're not commensurate, so if you just graph this out, you'd be looking at some kind of chaos, potentially. You're not really seeing anything. Okay? But we're going to tease out some important properties. Because remember, we already showed this was equivalent to the double pendulum, and the double pendulum showed us speeds. Right? So that's where we're headed. So anyway, the way to do this is now to define omegas on the number line, and since omega 1 is less than omega 2, I can just separate them like that, and right between here, I'm going to put omega. So what I'm going to have is omega equals omega 1 plus omega 2 divided by 2. And I'm going to define alpha equals omega 2 minus omega 1 divided by 2. This is an algebraic problem that we can solve geometrically, so it's kind of interesting in that regard. Okay? So there's my alpha, right? And because we can either do this geometrically or algebraically, or just looking at the picture, what we now get, just looking at the picture, is omega 1 is omega minus alpha, and omega 2 is omega plus alpha. So I've just redefined these two, or defined these two new frequencies, and expressed omega 1 and omega 2 in terms of them. just see it from the picture or you do the algebra, same thing. So next, we're going to go ahead and plug these in here and see what happens. Let's leave this picture up. And we'll get an interesting result. Probably primarily enough to work the top one here. So x1 of t, being careful to make this large enough. We have cos omega minus alpha t, so that would be cos omega, oh, sorry, not so fast. Cos omega t cos alpha t plus sine omega t sine alpha t, but that's the omega minus alpha. And for the omega 2, we have plus cos omega t cos alpha t minus sine omega t sine alpha t. And you'll notice that x2, let's leave a bunch of room between these two, okay? x2 of t, the difference between x1 of t and x2 of t is that I'm going to have a minus sign here. Where I have a plus sign here, I have a minus sign here. That's the only difference, because there's that minus sign. So what happens now is that sine omega t, sine alpha t cancels here. And I have two of these. So x1 of t equals x1, 0. And I'm going to write the cos alpha t first. You'll notice there hasn't been any, and I'll put a square bracket around it, cos omega t. Well, I haven't made any approximations yet. I've just done some redefining of places of brackets. To the x2 of t, what's going to subtract away is the cosines, and we're going to keep the sines. So we're going to have x1, 0. And again, I'm going to put the sine of alpha t, this in the square bracket, t, and the sine omega t. Okay, so this is a fantastic result. And I've just put it in that form because we're going to see some nice effects. So if alpha and omega are just as random as omega 1 and omega 2 in principle, okay? But we're interested in the case where k prime is small compared to k. Let's remind ourselves, omega 1, k over n, omega 2 through k plus 2 k prime over n. But now it's all on the board, we can start to contemplate it. If, this picture is actually good for that. If omega 1 and omega 2 are close together, because k prime is a very weak spring, then alpha is much, much smaller than the omega. Make sense? So these omega 1 and omega 2 are really close together, the alpha is much smaller than the omega because the zero's out here. So if the alpha is much smaller, then this is almost constant as this oscillates. Okay? So we can treat the square bracket as a slowly changing amplitude. And that's what I'm going to graph next. So we go ahead and erase these here. And this graph, we're going to do a careful zeros. So now let K prime be much less than K, so that omega 2 is greater than, but almost approximately, omega 1, which means that with those definitions I just showed you, alpha is much less than omega. That's off of the number line, okay? Alpha is much less than omega. So we're going to do a careful graphing. We're going to stack these. This is going to be x1 of t. This is going to be x2 of t. We're going to stack these graphs carefully. So if we just ignore this for a moment and graph the square bracket, we would have a cosine. So there's my x1, 0, and 1, 2, 3, 4. That will be a complete period. And then I could do a couple more for good measure. Okay? And what we'll do is make this envelope like this. Oops. And we have to go down here to the x2 and carefully match up these points as good as possible. Now x2, the square bracket, is the sign. So if we graph this one here with the sign, we're going here, here, there, and we'll make the envelope so what's happening, as we do another color, is that omega is much larger than alpha. And so we release it from rest, and the red motion is the actual motion of the first pendulum, right? This was 1, and this was 2. And it starts oscillating like this. And the amplitude decreases till it vanishes. So this is the actual motion of x1. The blue dotted lines are the fact that the amplitude is changing. And this is that limit where those, much weaker. Okay. So that was x1, and you do the same thing for x2. It starts at rest, and it starts to acquire more amplitude. Here's its maximum, which lines up with the minimum when this one comes to a dead stop. And so on and so forth. Okay, gotta love this graph, right? And so forth. And that was that phenomenon with the two pendula swinging back and forth. In the ideal case where there's no decay, it'll just keep going on forever. So this, again, this was a limit of small k prime with k, or small coupling of this. Generally, you're not going to see any pattern here. And yet it's there. So if you have a system that actually has two frequencies, which is what our system had, right? Our system had two different frequencies. What if those frequencies are audible? What are you going to hear? That's the beats phenomenon, right? You're going to hear that coming in and out. If you don't have the beats, so you're just going to hear two notes. You're going to hear two notes. Your ear is going to pick up the one frequency and the other. Even though, I should point out the general frequency pattern can be, very, it repeats itself, but it's really complicated. talked about Fourier analysis last semester. We were talking about, composition or decomposition of a signal in terms of many different frequencies. Good, so there you have it. This is a problem we took from beginning to end completely. You haven't even fill in those eigenvectors, right, that I made use of. Yeah, so this one you definitely want to have there in your notes. You can study this one and see everything that happened and be able to reproduce it for your friends at lunch sometime. On the menu. Okay. You can do that. I didn't bring any of the beats are, as Thomas just showed, they're really audible, and the same thing holds true. You actually have two frequencies that are very close together, but not exact, and you'll get that beat frequency. So the piano tuners use that. They don't somehow have the frequencies dialed in. They compare one frequency to another, and it's, musicians generally, they'll adjust the frequencies till the beats go away. If the beats go away, the alpha goes away, and the two omegas are the same. So we could bring some demos in possibly. They're downstairs in Conrad's area. Good. So what's next? May not have enough time, but we'll get it across. So what happens if instead of 2, we have 3, 4, 5? It gets really complicated. This one we can solve for 2. But instead of 3, 4, 5, we have 30, 40, 50. We can get something easy to come out of it again, okay, which is what we're going to do, okay? So we're going to talk about a chain of these masses. In fact, as an intermediate step, maybe I'll draw, 3 and 4. But then when we go to a long chain of masses, there's something simple that comes out of the mix. Okay, so we'll talk about that. As well, okay. Let's do this. So this one we took to completion. Now, you can make it as complicated as you want. Suppose we have 4 equal springs and 3 equal masses. Turns out this is one we could actually tackle. And it has some interesting properties as well. So there's the x-axis, no friction, 4 equal springs, even without, and x1, x2, x3, they all equal 0 when the springs are completely relaxed. They're sitting there in equilibrium. So there should be one frequency that we can guess. This system has 3 frequencies. I'll get it right, up to 3 frequencies. Some systems will have 3 frequencies, but 2 of them are the same. So I'm just gonna leave that right there. Can anybody guess what one of the frequencies is based on some of the principles we've been doing so far? K over M. That's too easy of an usher. That was not quite right.
I don't know if you can get a frequency for this, but can you have a scenario where the 2 on the ends are oscillating and the one in the middle is still?
That's the one we're looking for. So suppose the 2 on the end are oscillating, the one in the middle is still. That's going to turn out to be one of the eigenmodes, and the eigenvector, by the way, would be 1, 0, minus 1, right? Just like we had, makes sense, right? So the eigenvector would be 1, 0, minus 1. What would the frequency be if two are oscillating like this, the two endpoints? It's always great to solve the problem without doing the math, right?
Something like root 2k over m, maybe.
Close. So the point is, this one is going to be welded in place. So this outside spring is going to be K. This inside spring is going to be 2K because it's half a spring just by construction, right? This one's welded back and forth. Actually, before I say that, this one's fixed in place. These two are going against each other. 2K. 2K over M? This is just a supposition because we actually would have to prove it. A could be 1, 0, minus 1. And then this one is welded and these two are going against each other. What's 2K should be, right? Because of the symmetry of this is as though this one's nailed down and these two are doing their independent thing. Root 2K over M. So that's a guess based on physical principles. And if we were to set this one up, we'd have to see if that's true.
We did this one in math methods last semester.
In math methods, it was camouflaged because we didn't have the Lagrangian method yet. Right? So yeah, that's a good problem. And you can extend this and then it starts to get more and more complicated. This has a cubic, but because you can guess one of the answers, it's a solvable cubic. If you had 4 masses, 5 springs, it would be a quartic. And you can, unless you have some really nice symmetry on it, you can forget it. You can have problems. So, dot, dot, dot. I may assign this one. Yeah, let's assign this one. Put this in something that has in your notes, but it's nice to revisit. Okay. So let's add this one to the mix. So the homework is to find L Mij, Kij, and frequencies. We'll leave off the frequencies omega. Well, this is one that still works. Works pretty well. Okay, so this next one I'm just going to set up now. So, like I said, 3 just works, 4 you're in big trouble, 5, 6, 7, forget it, right? But if you have a large number of springs, there's a simplification that comes into play. So here I'm going to draw quite the collection here. I'm just going to put them all on a line. Dot, dot, dot. N equals many. So what would the Lagrangian be for these? So there's a spring between each one of these. Each one is K, little m, m. And the key is to, what's that, K, this the J, this is the J plus one, this is the J minus one. Because the Lagrange invariants are ideal physics springs, so Lagrangian has this form. Sum over 1/2 m x use k dot squared. Sum over k minus sum over 1/2 k x k squared. Clever use of k's, right? You gotta live with it. We use no one. And the only thing that's wrong about this expression is that the endpoints, at the distant endpoints, you know, we're saw it's connected and we don't have the difference. Oh, my bad, before we go. This was k x k plus 1 minus x k squared. Sorry. The point is that each mass kinetic energy, just as the small system, but each spring is storing the energy from being compressed by its nearest neighbors. And I'm just going to write k is large, so we can ignore the endpoints. Otherwise, we could say k equals, 1 to n, but then here would be k equals 2 to n minus 1, and we would add the n ones. Okay, so I'm not going to worry about that. But yeah, all we're saying is, because kinetic energy of the particle and potential energy is stored in the compressed spring, which depends on the nearest neighbors. So this is where I'm going to leave us. What we're going to do next time, this is a great calculation, we're going to write down the Euler-Lagrange equations, dl dxj dot minus dl dxj equals 0 for all j. Ignore the endpoints, because there's so many of them. We're somewhere in the middle, so we don't have to worry about that. And then we'll see some interesting stuff unfold here, because each of these equations only knows about the two neighbors of a single one. It really only knows about, for j, it only knows about j plus 1 and j minus 1. So we'll get a big series of equations that we'll then manipulate and get an interesting result for. That's the plan. So we're going to leave it right here. We'll see how much of this we do. We also want to do our eigenvectors on Friday and the other stuff that we're interested in. Good, that's all I got for you.